Yes, okay. I'm recording. That's good. Now, so let's start with the exponential. What's an exponential function? So I'm going to start with definition. I'm going to try to give you a couple of examples, and then we're going to study like some properties of exponential functions. I'm going to explain a bit of like properties of the graph of exponential. But as I said, we'll be really interested in how to solve exponential equations. All right, so let's start with the definition of exponential. So what's an exponential function? It's just a function of the form, and so definition. So it's a function, exponential function it's a function of the form b to the power x. So an exponential function. So exponential functions are functions of the form f of x. So f of x equal to b to the power x. So here, guys, the x, the variable x, is in the exponent, right? So the b, so where b, so b is supposed to be constant. So where b, it's a constant. Okay, and this b, this constant b, must be positive and different from 1. So with b, so it must be positive. This is really important. With b positive. And positive and different from 1. Different from 1 because 1 to the power x would be just equal to 1 anyway. It would be just a constant function. So different from 1. Okay. So examples. Before the example, so this number, this constant b, is called the base of the function, of the exponential function. So b is called, so the b, so b is called the base okay, the base of this exponential function is called the base. All right, so some examples. So first example, I'm gonna just take f of x equal to 2 to the power x. Okay, so as you can see, so whenever I have x in the exponent, that's actually an exponential function. That's what we call an exponential function, whenever x is in the exponent. Okay, so the base here, b, is equal to 2. So this is an exponential function, is exponential with base b equal to 2. So the base b is equal to 2. Okay, that's an example. So of course, so let's say when I evaluate f of 3, that will be like 2 cubed. That will be 8. So if you want to evaluate, let's say, f of 6, that will be 2 to the power 6, right? So the variable x is the exponent. 2 to the power x, which is actually 8 times 8, that's 64, etc. Right? Another example of exponential function. So this base b could be, of course, could be fraction, right? So, for example, half to the power x. Okay, this is also an exponential. So is exponential with base b equal to half. Okay, so for example, we want to do, or we want to find f of t. F of t would be like half to the power t, or cube half to the power t. So that's like the power here, guys. I mean, this is equal, because of the parentheses, this is like half, times half times half. So there'll be 1/8, 1/8, right? That's f of t. It could be a fraction. Your base b could be a fraction. It could be a decimal, of course. So example number 3. F of x equal to, for example, or it could be a square root, right? So it could be, for example, square root of 2 to the power x. Okay, that's another example of exponential. Is an exponential function with b equal to the square root of 2. Okay. So b, base b, it has to be positive. That's the important thing. Different from 1. It could be a whole number. It could be fraction. It could be square root or decimal, etc. A non-exponential example would be like, for example, f of x. If you take a negative number, so or negative constant, like negative 2 to the power x. So this is not exponential. That's not what I call an exponential function. Okay, it's not exponential because your b is negative. So b cannot be negative. That's really important because you may ask why b, it has to be positive, not negative. Because if you have a negative number and x is, variable x is equal to, for example, half, then, negative 2 to the power half, that's like saying square root of negative 2, and square root of negative 2, of course, it's not a real number, right? The square root of negative 2, it's not a real number, right? So b cannot be negative. Okay. We may have like a function of the form 5. You may have a function of the form f of x, like x to the power x. I mean, that's possible. For example, you want to do f of phi, there'll be like phi to the power phi, it'll be a1. Sorry, what was that? Oh, sorry. That's 27. So that's 3 times t, that's phi, that's 27. For example, you can do f of 2, that's like 2 power 2, and that will be 4, etc. Right? You can have like f f of x equal to x to the power x, right? And if you have x to the power x, so here you see x to the power x, x is the x is the power, x is the exponent, and x is also the base. Okay. But such function is not exponential. This is not exponential because the base b, it must be constant. Here, as you can see, the base b is not function. Your base b, your base is not sorry, the base is not a constant, right? So if the base is not constant, then it's not an exponential function. So this is not exponential because the base b is not constant. Because the base b is equal to x, and that's not a constant. X is a variable, right? The value of x changes, right? It's not constant. Okay, so that's yeah. One more thing, guys. As I said, if the base b is equal to 1, 1 to the power x is equal to 1, and that's a constant function. That's not an exponential, right? So let me just say here, number 6, if you have like f of x Like as I said, this is 1 to the power x. The problem is that 1 to the power x is just equal to 1. It doesn't matter x. For any x, 1 to the power x is 1, and this is constant. It's not. This is a constant. This is a constant function, so it's not. It is constant, so it's not exponential. So it's not exponential. All right.
Wait, it's constant, but it's not exponential.
No, we don't count the constant function as an exponential.
Huh?
So it's constant. It's not exponential. Because 1 to the power x, 1 to the power x is always equal to 1. Doesn't matter x. That's always 1. So it's constant. Doesn't change the value of the function f. Does this answer your question?
Okay. Yeah.
So yeah, it's constant. It's a constant function, so it's not an exponential function. All right. So yeah, yeah. So that's what I mean by exponential. One last example, and very important example. I mean, I don't know if there's a really natural way to introduce this, but there is a very special number. There is a very special number called the number e. And I'm going to explain why this number is very special number.
For 6, you put it's constant, it's not an exponent?
Yeah, it's not exponential.
Oh.
It's not an exponential function. So it's constant. It's a constant function. So it's not an exponential function. It's not an exponential function. The I mean exponential, not just the exponent. Yeah. Yeah, I was saying this is a very special number called number e, exponential actually, called the number e. So the number e. So this number e is actually equal to it's a decimal number. This is a decimal number. This is decimal. And I mean, it's actually equal to like 2.7182. Okay, 2.7182, etc. So what's the special about this number? Well, the special thing is that so if we take f of x equal to this number e, so e to the x. Again, this e, it's like a decimal. It's like 2.7 something. So if you take e to the x, so this is an exponential function, of course, because you have some constant. As I said, the constant b could be, yeah, it's like a constant, like a pi, absolutely, Raviu. Yeah, it's a very special, like the number pi. And so this is an exponential function because, I mean, my constant b is just equal to this decimal. And as I said, the b could be whole number, it could be fraction, could be decimal. So this is an exponential function. But what's special about this exponential function? So if you take this f of x, then the derivative, and you will see this in the in Calc 1. Of course, we are not doing the derivative in pre-calc. Then the derivative of f of x, then the derivative of f of x is f of x. Okay, that's the very special thing about this number. It's equal to its own derivative. So the derivative of this function f is equal to the same function. That's very special. And again, we'll see this. You will see this in Calc 1. All right. So this is in Calc 1. Okay. So, but anyway, so all you need to know, guys, for this section is that there's this special number E, which is 2.7 something. And this number E, we're gonna use it later to solve our log exponential and log equations. Anyway, so this is this f of x equal to e to the x. This is, of course, this is what I will call, like, this is a natural exponential function. This is the natural natural exponential function. Okay. All right. So this is just some examples. Now I'm going to give you some properties of this exponential function, right? So properties of this exponential function and some properties of its graph. So properties of f of x equal to the b to the x. All right, so it's just some the properties here is just some like power rules. So for example, f of 0, that's b to the 0, which is of course equal to 1, right? Number 2, if you have like b to the x times b to the y, right? Then that will be equal. So here we have like the same base, right? This the base here is the same, which means that this number b is the same. Okay, so this is because we have the same base b, base b. Okay, so if you multiply two numbers with the same base, then that will be b to the power, and then you're gonna add the powers, right? So that will be b to the power x plus y. Okay, so if you multiply two numbers with the same base, two exponential with the same base, then you're gonna add the powers. If you divide two exponential with the same base, you know, if you have like b to the x over b to the y, so this is like division of two exponential with the same base. So here we have the same base. Then so there'll be b to the power x minus y, right? So the power in the denominator comes with a minus sign, right? So it's x minus y. All right, and last property, number 4. So this is just
Why does it become a negative, Professor?
yeah, because as I said, because this y is in the denominator, right? You see this y here in the denominator, and to move a power to the top, when you move a power to the top, it becomes like the opposite. So if you have plus y as a power in the bottom, when you move it to the top, it would be minus y.
Okay.
Okay. Sure. And yeah, and the last property of this exponential is like when you have so if you have like two different exponentials, so let's say you have like a to the power x over b to the power x. Okay, so here it's the same exponent but different base, right? The base is different here, so this is equal. So same exponent, same exponent or same power, as the power is x, but different bases. So you have different bases. So then that will be so you can you can pull out the exponent x. So there'll be like a over b, the whole thing to the power x. Okay, so if you have an exponent, a common exponent, then you can sort of pull out the exponent. So then your whole fraction would be to the power x. Anyway, so this is just some properties of the exponential. I mean, you are probably aware of these rules. Now, next thing, we're gonna discuss a little bit or some properties of the graph of exponential. So next, some properties of the graph of exponential. So in this section, I mean, we won't do a lot of graphing. I'm gonna just discuss a little bit like the domain first. So what will be the domain of the exponential? So f of x is b to the power x, right? So the domain here, the input x, because of course b is positive, so x here can be any real number. So the power x, it can be a whole number, it could be a decimal, a fraction, negative, it doesn't matter, right? So the power x here can be really any real number. So the domain is any real number. So the domain here is the whole number line. It's negative infinity, positive infinity, because the power x can be any real number, because x or the exponent x or the power x can be any real number, can be any real number. Okay, because I mean, if you have some negative power, or you have like a fraction as a power, you can still evaluate your exponential. It's there's no problem. Now, what will be the range? Well, here the range, it's a b to the x. So because b is positive, then b to the x, it doesn't matter if x is negative or x is positive. B to the x, it's going to be a positive number, okay, because b is positive. So the range here is actually any positive number. So it's like 0, positive, infinity, because b is positive. So then b of x is, b to the x is positive. All right. What will be an x-intercept for the exponential function? So, well, I mean, f of x is, so x-intercept. Well, so we're supposed to solve, f of x, which is b to the x, equal to 0, right? That's how we find the x-intercept. But b to the x, but as I said, b is a positive number, and if you take the power of any positive number, it's gonna be positive. So it cannot be 0. There's no solutions to this equation. Okay, so b to the x is gonna be always positive because b is positive. So there is no solution. There is no solution because so b to the x cannot be 0. So there is no solution because b to the x is always positive. It is always positive for any x. It is always positive for any x. So for any x. So so here there's no x-intercept. So exponential functions, they don't have an x-intercept. So exponential function.
Professor,
Yes.
I'm sorry, can you put it
Yeah.
down just one more second so I can, thank you.
Sure.
All right, I'm good. I just took a screenshot. Thank you.
Yeah, no problem. No problem. So yeah, f of x, the exponential function has no x-intercept. X. This is x. It's not alpha. So this has x. Has no x-intercept. Okay. Now, what will be y-intercept for the y-intercept for the exponential function? Well, we just evaluate f of 0, and f of 0, that's b to the 0, and that will be equal to 1. So we have y-intercept at 1. So for the y-intercept, so we evaluate f of 0, and f of 0 is just b to the 0, and that will be equal to 1. And so f of x, the exponential function, has a y-intercept, which is 1. All right. What else? Yes. Anyway, so if you try to use all these informations, to graph exponential, I'm gonna just give you an idea about the shape of the graph of an exponential. So, an example here. I mean, this is just for you guys, so what will be the shape of an exponential. So, for example, if you have the e to the x, remember this is a special natural number exponential, e to the x. So the graph of e to the x would be like. So as I said, there's no x-intercept. The domain is any real number. The range is positive numbers. There's a y-intercept at the 1. This is a 1 here. All right. And of course, I mean, because we are not, you're going to see this in Calc 1, you'll see that the exponential function is actually an increasing function because of its derivative. But anyway, so the graph of the exponential function is going to look like this, something like this. Okay, so this is the graph of the exponential function. Okay. Here, of course, there's no intersection, right? There's no intersection because there's no x-intercept. So here there's no intersection with the x-axis because there's no x-intercept. So the graph of exponential functions, or the exponential function is, as you can see, is an increasing function. Okay. Anyway, so it's just to give you an idea about the graph of an exponential function. Okay, so that's for the exponential, and then we're gonna define the inverse, like a coronavirus. Yes, exponential, absolutely, Rabiul. Yeah, you can modelize like the coronavirus. Yeah, this exponential function. Yeah, transmission. Yes, of the virus with an exponential function. But you're gonna do this. I mean, if you take Calc 1 and you take I think Math 31 and you take Math 34, you can see there how we modelize like the propagation of the transmission of the virus using this exponential function. But anyway, okay, so now what we're gonna do, guys, we have this exponential function. It's just a function of the form b to the x. B is positive, okay, and then we're gonna define the inverse. So this function here, as you can see from the graph, if you do the horizontal line test, remember, if you do the horizontal line test, and if your horizontal line doesn't intersect the graph at no more than 1 point, then the function has an inverse. And the exponential functions, they do have an inverse. So, and the inverse of an exponential function, that's what we call the logarithmic functions. So my claim here is that so exponential functions, they have inverses. So f of x equal to b to the x has an inverse because it passes the horizontal line test. And that's actually a definition of the logarithmic function. That's the inverse of the exponential function. So the inverse. So the inverse of f of x equal to b to the x is g of x equal to the log in base b. So here it's an exponential function with the base b, log in base b of x. Okay, and with x, so the x here, it has to be positive with x positive. Because as you can see, guys, here there's a problem with the inverse. There will be a problem with the inverse here when x is negative. So we need the x to be positive. So what do we mean by this log to be the inverse of the exponential? Well, so in other words, so remember definition of the inverse. So g is the inverse of f if like f of g of x is equal to x and g of f of x is equal to x, right? That's what, so this is when g, so here g is the inverse of f, right? That's how we define the inverse of a function f, right? So if you do f of g of x, that will be equal to x. So here in this case, like, so if you want to compute f of g of x, right? So f of x is supposed to be, that's my b to the x, right? Now I'm saying g, the inverse is this log. So g of x is this log in base b. Now, if you do f of g, so you have to replace, this x here with the g, with this g. Okay, so that'll be like b, right, to the g, right? So b to the g of x. So that will be equal to b to the power log in base b of x. And this is supposed to be equal to x, right? That's by definition of the inverse. F of g of x is equal to x. So what we are saying here, guys, is that, so this is like the first identity is that, so b, so if you have b to the power log in base b of x, that's supposed to be equal to x. And this is exactly what I'm saying by exponential being the inverse of the log, because this is like your log and this is like your exponential in base b. And what we are saying is that this b and this log and this exponential and this log, they are inverse of each other, right? So you end up with x, right? So let me write it again here. So this is the first identity because of the definition of the log. So b to the power log in base b of x is equal to x. Now, there's another identity, right? Because g is the inverse of f. So first, we know that f of g of x is equal to x. And we also know that g of f of x is equal to x. And so now, g of f of x, this is supposed to be equal It's getting crazy. No, it's not that crazy. It's just a definition. I mean, you have this exponential b to the x, and then you define the inverse. You have this in inverse, which is defined by log, right? And it's just a consequence of the definition, because f of g of x is equal to x and g of f of x is equal to x. As you can see here, so g of x, it's by definition, it's log in base b of x. So you substitute x with the f, right? This x here with the f, right? So now it's going to be like log in base b of f, and f, let me write it down here, f of x. And what's f? F is the b to the x, right? So this is equal to log in base b of b to the x. And that's by definition of the inverse. This is supposed to be equal to x. So another identity here is that, so if you have log in base b of exponential of x, that will be equal to x. No. We cannot skip this for the final.
Did you repeat that? Did you repeat it?
We getting dizzy over here, Professor.
Oh, did you
It's like we're spinning.
Everything
No,
was
no.
good until they hit the inverse.
wait? You
well, no, it's you know, because of the definitions. You see, when I say this is my log, right? That's my log, and this is my exponential. And like when I say log is the inverse of the exponential, kind of, it's like saying they cancel out, and then you end up with x. So like this log here and this exponential, they will cancel out, and then you end up with this x here. Okay, so that's like saying that's what I mean by the inverse. F of g of x, so the f, f of g of x is equal to x. This is like saying f and g, they cancel out, and you are left with x. All right, that's like the idea behind the inverse. So f and g, they go away, and then you are left with x. Yeah. With the examples, yeah. We see with the examples, yeah, we're gonna do a lot of examples. You see, it's not that crazy. Let me just write it again here. So we have this. So here we are saying, so log in base b of b to the x is equal to x. Okay, let's do some examples. Some examples. Okay, first example. So what we are saying is like, if you have like 2 to the power, let's say log in base 2 of x, okay, then that will be equal to x. Okay, so you see, when you have 2 here, this is your base, right? This is exponential, and you have your log, okay, the exponent. So then because the exponential and the log, they are inverse of each other, then you end up with you are left with x. So that will be equal to x. Or the other way, if you start with the log, like in base 2 to the power, the log in base 2 of let's say 2 to the power x, that will be equal to x. So this log, guys, it's just it's just a function. I mean, it's not for example, when you say log in base 2 of phi, okay. I mean, you can check your calculator. There's this for the function log, okay, and in base 2, for example. So this log in base 2 of phi, this is a number. So let's say it's 1 point, I'm not sure, but I don't have my calculator, but I think it's 1 point something. But anyway, it's not, it's just for example, I think 1.51 or something. So log in base 2 of phi, it's just a number. Of course, when you change the base, for example, if you do log in base 2 of 4, that will be a different number. So that will be probably, I think, 1.7 or something. Okay, so that will be another decimal. So log in base 2 of a number, it's just some decimal. It's not like I mean, it's just a number, right? Okay. Yeah. Before that, yeah. Let's do. No, that's not true, Sean.
Isn't the 2 there the base and the 3 is
No. No, it's okay. So let me do the following remark. So here's a remark. So if you have, let's say you have y equal to log in base b of x, okay, then b to the y is equal to x. So for example, okay, so for example, let's say you have examples. So let's say you want to solve for x. Log in base 9 of x equal to 6. Okay. Log in base 9 of x is equal to 6. So we want to solve for x, right? You want to solve for x. So how can we do that, guys? I mean, the problem, of course, is this log, right? And you want to get rid of the log. All you have to keep in mind, guys, is that if you want to get rid of the log, just apply exponential, because exponential and log, they are inverse of each other. So if they're supposed to cancel out. So I have this log. I want to get rid of this log. So the way to do it is to apply exponential. Apply exponential to get rid of the log. All right. So I'm gonna apply exponential at the same base. So as you can see, this is log in base 9, right? This is log in base 9. So I'm gonna apply exponential. There's 9 here, okay? And I'm gonna put this as a power. So this log here and this 6 as a power. So this is 9 to the power log in base 9 of x. And on the other side is it's a 6. All right, so now the thing, guys, is that as I said, this is a log and this is exponential in the same base. This is exponential in base 9, exponential in base 9, and this is a log in base 9. In base 9. So then the exponential and the log, they cancel out. So then now it's just x on the left side. So this is just x. So then x is equal to 9 to the power 6. What you are saying, guys, in the chat? Yeah, it's 9 power 6, Rabiul. Yeah, it's like 6,000 and yeah, probably 6,000 something. Yeah.
Oh, I thought that was a cube.
Oh, a cube. Oh, okay.
Wait, wait, that's not a cube? Wait.
Uh, where's the cube? I don't see the cube.
Oh, no. I thought that was a cube. Never mind. Yeah.
Oh, cube. Sorry. No, it's a 9. It's a 9.
Okay.
It's a 9. I mean, here it was log in base 9.
Okay.
Right. Another
So-
example. Yes.
No, sorry, go ahead with the next one. I'll probably.
Yeah.
jump on the next
I'm gonna do a lot of examples. Don't worry about that. So let's say let's say we have like log in base 2 of x equal to, let's say, 3. And again, I want to solve for x. So this is the log. Just apply exponential. Again, exponential in the same base. In the same base. So the base here it's 2, right? This is log in base 2. So the base is 2. So I'm going to put 2 both sides. Here the power. This is exponential, so it's like a b to the power b to the some power, right? So b is 2. So b to the power, here on the left I have b to the power log in base 2 of x, and on the right it's 3, so it's b to the power 3. Okay. So well, then this is exponential in base b, and this is a log in base b. They cancel out, so it's just x now on the left. So it's equal to x on the left, and that'll be 2 cubed, which is of course 8. So x is equal to 8. So the idea here, guys, I mean, for this logarithmic equations, whenever you have log, get rid of the log by applying exponential. Yes, yes, Elizabeth.
So for the final answer, you want the 8 or the 3 or the 2 in the third?
So no, the final answer is x equal to 2 cubed, which is 8. So the final answer should be 8.
Eight. Because I was confused if we want to put the first
The
or the
2
second.
cube,
The 2 cube.
no, final answer would be 8. Yes.
But we have to put the process like 2.
Yeah, of course.
Use the 8.
You mean you have to explain the steps? Yeah. I mean, here I didn't compute the 9 to the power 6 because it's a very large number. But yeah, you have to compute your power, and that will be your answer.
So what
Um,
you had pretty much the same number as you have as your base,
yes,
pretty much,
yes,
just to cancel out.
that's the idea. Yes, just apply the same exponential the same base. If it's a base 2, you need the exponential base 2. Yeah, same base. Yeah, absolutely. Another example, let's say you want to solve
That seems to be easy.
so let's say you have log and you want to compute let's say log in base 7 of 49. Let's say this is equal to x, and you want to find your x, right? You want to compute log in base 7 of 49. Again, this is not a multiplication, guys. This is not log times 49. It's log of 49. Log of 49 it's a some number. A log itself, it's just a function. Okay, log. This is, I think, a common mistake. I mean, log of like log of 7. This is not like log times 7. It's not multiplication here. It's this is like a composition. Okay, so it's log of 7. So a log of 7 would be some number. Log itself, just log, it's just a function. Okay, so this is not a multiplication here. This is not a multiplication. It's log of, right? Like f of g of x. It's composition. Anyway, so we want to solve for x. Yeah, 7 is the base. this is a 7 is the base, sorry. So 7 is the base. So I wanna find this x. So as I said, get rid of the log, just apply the exponential the same base. So apply exponential the same base, which is 7.
Mhm.
So that would be, so here's my exponential. So when I say exponential, guys, it means like a number to some power, right? So here's my exponential base 7 means the number 7 to some power. So the power here, I'm gonna put like the two sides of the equation. So here it's log in base 7, 49, and the other power here would be x. All right, so log in base 7 and the exponential in base 7, they cancel out. So it's just 49 on the left. And on the right, it's 7 to the power x. And again, the question is, what will be 7 here? Sorry, what will be x? We are solving for x, right? So for which power of x, 7 to the power x would be equal to 49? That's a square, right? 7 square. So, but 7 square is equal to 49. So then x is, so then solution here, x is equal to 2.
Yes.
Okay. Yeah, another example. I think example 4. And example 4. Let's say you have log in okay, log in base log of base 2 of 2 to the power x equal to 1/8. Okay, and again, you want to solve for x. Solve for x. Okay. Let's just take a 2 to the power x here. I'm gonna just take not 1/8. I'm gonna just take yeah, I'm gonna just take 2 to the power x, not the log, without the log. Now let's change from so let's change and take some exponential equations. So let's say you have 2 to the power x equal to 1/8. So as you can see, guys, here, this is an exponential, right? This is an exponential function with the base 2, exponential. And so here, 2 to the power x equal to 1/8. And you want to solve for x. The thing is, you can write this 1/8 as like 1 over, I mean, 8 is 2 cubed, right? And 1 over 2 cubed, that will be equal to 2 to the power, yes, Lorden. So if you move this power 3 to the top, that will be -3. So that's 2 to the power -3. All right, this is 2 to the power -3. All right, so we are trying to solve 2 to the power x equal to 2 to the power -3, right? Because whenever you have the same base, right, this is the same base, okay, then the powers are equal. If you have the same base, then the powers are equal. So same base, then the powers are equal. So same base. Yes, Lorden, absolutely. So this is the same base, then the powers are equal. Okay, so then x would be equal to -3. Okay. Um, now
Why,
you may
why I
ask
feel like this is two different,
from the previous one. Yeah, it's different actually. We did just some log. Sorry, we did some log equations here. This is like an exponential equation, so there's no log here, right? Here before, I mean, in the previous examples, we had like just like some log equal to a number, and we had to solve for x, right? So that was like a logarithmic equation.
Right.
It's like you have log, right? Here we have like an exponential equation, so it's like there's no log here, and you have to solve for x. So if there was a log, as you can see in this example, if there was a log, then you apply exponential in same base to get rid of the log, right? And now what I'm saying is that, so in this example, there's no log, it's just some exponential, 2 to the power x, and you are trying to solve for x. So I didn't apply any log here.
Got
I have a question.
Yes, please.
How did you get -3? I don't.
Yeah, -3 because okay, so what I was saying, it's 2 to the power x equal to 1/8, right? And then I said 8 is 2 cubed, right? 2 times 2 times 2, that's 3 times. 2 multiplied by itself 3 times. But then 2 cubed, it's in the denominator, but if you want to move it to the top, you have to take the opposite power. So that will be 2 to the power -3. So what I end up here is I end up with 2 to the power x equal to the 2 to the power -3. Okay, and now what I was saying is if we have the same base, which is 2, okay, then the powers are equal. So that's why my x is -3.
Okay, thank you.
All right, guys. It's just some examples. It's just some examples, but let me give you more some properties of this log function, right? I'm gonna say yeah. So yeah, some properties of the log. This is f of x equal to log in base b of x. Okay. Again, this log in base b is supposed to be the inverse of the exponential with the base b to the x. So first property, guys, is that if you do what will be log in base b of 1? All right. Well, let's say this is log in base b of 1 is equal to some number, is equal to x, and I want to solve for x, right? So how we do that? Well, there's this log in base b, so you apply exponential to get it of the log. Apply exponential in the same base. Okay, so that'll be the base here, it's b, right? So I'm gonna have b here, I'm gonna have b here, this is equal, and the power, so here on the left I have this log in base b of 1, and on the right that's x, right? So on the left we're gonna have so this b exponential in base b and this log in base b, they cancel out, right? So on the left we end up with 1 here, and that will be equal to b to the power x. So for which power of x b to the x is equal to 1? Well, there's only one possibility, which is 0, right? Because but b to the power 0 is 1. So then my x must be equal to 1. Okay, so what we are saying here, the first property is that log of 1, sorry, then x is a 0. Sorry, this is 0. Then x is 0, of course. Right, because I'm saying b to the 0 is equal to 1. This is b to the 0. So x is 0. Right, there x is 0. Right, this x here is 0. So first property of the log is that log of 1 in any base is 0. So a conclusion here. So log in base b of 1 is 0. And that's because b to the 0 is equal to 1. So what you need to keep in mind, guys, log of 1 in any base is 0. It's just the number 0. Number 2, next property, log in base b of b. Number 2. So what will be log in base b of b? Okay. So let's suppose this is, again, let's suppose this is x, all right? And we want to solve for x, right? You want to find what's this log in base b of b. So I'm going to apply again this exponential in base b. Apply exponential in the same base, which is the base b. So we're going to have like base b here, going to have base b here. This is equal. And then the powers. So on the left, I'm going to have this power log base b of b. And on the right side, I have x. So as usual, the exponential and the log here, they cancel out. So on the left, it's just b. So it's equal to b here. And on the right, it's b to the x. So then what will be x? Well, I mean, b is, it's b to the power 1, right? B is equal to b to the power 1. So this is like, it's like you have power 1 here, right? This is like power 1. So then x would be equal to 1. So then x is equal to 1. Right? So what we are saying is that log in base b of b. So if you, so inside the log, you have the same number as the base. The answer would be 1. So conclusion. So log in base b of b is equal to 1. Okay. Right. More properties. Yes.
And you cross out the b though, but you put b over 1.
No, it's not b over 1. It's b to the power.
Yeah, b to the power 1. Yes, what I meant.
Yes, but
You cross
so,
out the
no,
b though.
yeah. So because I got b, right? This log and this exponential, right? This log here. Oops. This log here and this exponential, they cancel out. So you're just left with this b here, right?
Oh, yeah,
And what I'm, excuse me?
okay, no, sorry, yeah.
Yeah, and I'm saying, so b is equal to b to the x, right? So when you have the same base, so if you have an equation with the same base, then the powers are equal, right? This is the same base. The base here is b, right? And the base here is b. So if you have the same base, then the powers are equal. Same base, then powers are equal. Okay. So it's like saying it's like saying I have like 2 cubed equal to 2 to the x, right? Then what will be x? Well, x would be 3 because it's the same base. Then the powers, they must be equal. And this b, when you write b, it's like b to the, you can say it's b to the power 1, right? So that's what I'm saying. This b is like b to the power 1. That's why x is 1. All right. So more properties of this log. I mean, like with what we did. Remember what we did for exponential? Like when you multiply exponential functions with the same base, then you will add the powers, etc. The same for the log. So next, so if you have a log, in base b of x times y, okay, then this is actually equal to log in base b of x plus log in base b of y. Okay, so what we are saying here, guys, is that log of a product is the sum of the logs. Okay, so if you have a log of a product, that will be the sum of the logs. And well, you may ask why this is true. Well, that's because because of the definition of a log, because it's the inverse of the exponential. Remember, for the exponential, if you have b to the x times b to the y, we said this is b to the x plus y, right? So if you have a product of exponential, the product of exponential, that will be the exponential of the sum. So this is like the product of exponential. That's the exponential of the sum. So for the log, it's like the converse, right? Because the log is supposed to be the inverse of the exponential. So for the log, the log of product would be the sum of the logs. Okay, so this property is just from the definition of the log as the inverse of the exponential. Okay. And this property actually is going to be very useful for us, because we're going to use it to solve some logarithmic equations. Next, if you have a log of division, so if you divide, so number 4, again, all these properties, they're just like a consequence of the fact that the log is the inverse of the exponential. If you have a log of x over y in base b, so if you have a log of some division, then there will be the difference of the logs. So there'll be log in base b of x minus the log in base b of y. Okay, and the last property of the log is so when you have a log in base b of x to the power a. So if you have inside the log, if you have like x to some power a, then what happens, guys, is that you can pull out this power a and you can put it in the front of the log. So that'll be equal to actually a. So this power here, you can pull out this power and you can put it like in the front of the log. So this is a times log in base b of x. Okay. All right, so let's do some examples and an exercise. So examples. So first example, so let's say log of x in base 2 is equal to 3, and log in base 2 of y is equal to 4. Okay, this is just given. It's given by the problem, and you want to find out log. So it will be log in base 2 of x times y. Okay. So you know log of x in base 2 is 3, log of y in base 2 is 4, and you want to find or evaluate the log of x times y in base 2. So what we do, guys, we're gonna use the second the third property. So in the third property, we said log in base b of x times y, that'll be the sum of the logs. So this log, so we're gonna use property number 3. Okay, which says that, so it says that log in base 2 of xy, this is log in base 2 of x plus log in base 2 of y. And the thing is, we know what's log in base 2 of x is equal to 3, and log in base 2 of y is equal to 4. So this number here, this log of x in base 2, this is equal to the number 3, plus, and this log in base 2 of y, we know it's equal to 4 because it's given, right? It's given the problem. So that's 4. So then the answer here would be 7. Okay. Okay, one more example, another example. Examples. Next, so let's say you know log in base 2 of x. Let's say it's again 3. Log in base 2 of y is let's say this time it's equal to let's say well 4 again, let's say, and you want to find log in base 2 of x over y. Okay, so as I said, for the division, guys, if you have a log of a quotient, then there will be the difference between the logs, right? This property number 4, log of the quotient, the x over y, that's the difference between the log of x with the log of y. So this log in base 2 of x over y, so using the property number 4, number 4, so this log in base 2 of x over y, that's log in base 2 of x minus log in base 2 of y. Okay, so then log in base 2 of x, it's given, it's equal to 3, right? This is equal to 3 minus, and log in base 2 of y, it's also given, and it's equal to 4. So the answer 3 minus 4, that's -1. So that will be the log of x over y in base 2. One more example before the exercise, guys. So let's say you have a third example. So you have log in base, let's say base 2 of x is equal to, let's say 4. Okay, and you want to find log in base 2 of let's say of x cubed. So you know the log of x in base 2, which is 4, but now we want to find the log of x cubed. So how do we do that? Well, So we're gonna use the last property, the property number 5, when you have x to some power inside the log. As you can see, if you have x log of x to some power a, then you can put the power a in front of the log, right? So what I'm saying here is that so this log, so if this log in base 2 of x cubed, this is actually, so I can move this, I can put this, put down this power 3 in front of the log. So there'll be 3 times log in base 2 of x. Okay, you put down the 3, so it's just now log in base 2 of x. But then log in base 2 of x, it's 4. So this is actually equal to 3 times 4. And 3 times 4, of course, would be 12. So the answer is 12. So you see, guys, if you have like inside the log some power of x, then you can always put down the power in front of the log. Okay, so an exercise, guys, for you. So we can just practice a little bit this log. So exercise number 1. Exercise 1. So we need to solve for x first. Okay, so we need to find log. So we have log in base, let's say 2 of x is equal to, let's say 3. All right, you need to find x. 2, let's say you have log in base 3 of 81 equal to x. Okay, that's the first exercise. So here we need to solve for x, guys. Second exercise, exercise number 2. So for number 1, so let's say log in base 3 of x is equal to 2, and log in base 3 of y is equal to let's say 4. All right, so please try to find the following. So I need to find, so first log in base 3 of x times y, 2 log in base 3 of y over x, 3 log in base 3 of x over y, and 4 log in base 3 of x cubed over y squared. Right, guys? Okay, so let's say you have 5 minutes to think about this exercise. All right, guys. Does anyone need more time? So, Lorden, you're saying for number one, let's see. X would be 8, which is very good. That's correct answer. And number 2, X is 4, which is also correct. Yeah, very good. Okay, so yeah, I'm gonna go over probably the first exercise. I guess you're done. Oh, sorry about that, Lorden. The brain too. I don't know if you do wear like glasses or something. I mean, if your eyes hurt, I guess probably. Okay, yeah. Me too. I mean, after like 4 hours, it's like it's like blurry. I don't I don't. Uh, yeah, it's hard to see after like 4 hours. Yeah, I know. Uh, all right. All right. So for um, oh wow, from 9 to 5, and then 6 to 10. Oh wow, Joel, that's a lot. All day on the yeah on the PC. Yeah, that's a lot. I mean, guys, that's I know. I mean, yeah, that's a lot. I guess no, everyone is like wearing glasses. I mean, there is no other way. I mean, yeah. So wow, yeah, well, that's very brave. That's very brave for you guys. That's a lot. Um, yeah, I'm sure. I mean, with the kids. Oh yeah, tell me about the kids. I actually I have a baby and 6 months baby, and it's like it's, oh yes, of course, yeah, I do have a baby.
Sleep at night?
Oh yeah, well he yeah, I mean, but
Congratulations.
no, he sleeps like at 7, around 7.
Okay,
Uh,
good.
yeah, he's a good sleeper. Yeah, that's yeah, yeah. But I mean, my wife she works too. I mean, I mean, we don't have time. It's like it's crazy. Uh, yeah. Thank you, Melody. All right, guys. Okay, so let's go over this before uh, before the
We have
time.
Kind of got stuck.
to send the homework, Professor?
Excuse me.
For the homework.
Yes.
Until tonight?
Oh yeah, it's due before midnight. Yes.
Okay. Okay.
Yes, please. All right. So for number one, so this log in base 2 of x equal to 3. So as I said, guys, whenever I have log and when I solve for x, just get rid of the log by applying exponential. So apply exponential, and in the same base, which is 2. Right, so my base here it's 2, so I'm gonna put 2 here, 2 here. On the left, it's a power log in base 2 of x, and on the right, it's 3. So that'll be 2 cubed on the left. And then the exponential, as I said, so exponential, this is exponential on base 2, and this is my log in base 2, they cancel out. So now it's just x on the left and equal to 2 cubed, which is 8. So the answer would be 8, as Lorden said. So the answer, final answer, x is equal to 8. For number 2, it's log it's log in base 3 of 81 equal to x. So log, this is number 2, log in base 3 of 81 equal to x. Actually, there are different ways to solve this. Of course, you can always apply the same trick, which is the exponential, the same base to get rid of the log. Same base. My base is 3, so I got 3 here on the left. I got 3 on the right, and the powers, the exponents. So exponent here is this log in base 3 of 81, and the exponent on the right is the x, and then my exponential base 3 and the log base 3, they cancel out. So now it's just 81 on the left, and that's 3 to the power x on the right. So the question is, for which power of x 3 to the power x is equal to 81? Well, I mean, 3 to the power 4, yes. So this 81, this is 3 to the power, so this is 3 to the power 4, right? So again, when you have the same base, so the same bases, right? It's a base 3, so then the powers are equal. So same bases, powers are equal. So your x is 4. Powers are equal. All right, so then x is this 4. All right, so this 4 here is equal to this x. Okay, just let me say, guys, here, another way to do it. I mean, if you don't like this exponential thing, which is, I think it's not, I mean, it's a good idea just to apply this exponential anytime you have a log. But another way to solve this, so we want to compute log in base 3 of 81, right? So then you can say this is equal to, we know that this is log in base 3. We know that 81, it's 3 to the power 4, right? And that will be equal. So remember, guys, we said if you have some power inside the log, then you can put down this power in front of the log. So this is like, now this is like 4 times log in base 3 of 3. Now, what's log in base 3 of 3? Well, remember we said one of the property of the logs, log in base b of b is 1. Yes, very good, Lorden. So log in base b of b is 1. So this is log of 3 in base 3, that's equal to 1. So this is actually 4 times 1. And so the answer, of course, is again 4. I mean, again, this is just another way to solve the problem. I mean, we are using different, like we are using like different properties, right? We are using this, having this power 4 inside the log. You can put it down in front of the log, and we are also using the fact that log of b in base b is equal to 1. Yeah. Both ways are correct, of course. In the last 6 minutes, let's go over the exercise number 2. So for the exercise number 2, so we know that this, we have this log in base 3 of x, which is equal to so is equal to 2, and log in base 3 of y is 4. This is 2, and log in base 3 of x is equal to 4. So first, we need log in base 3 of I think x times y, right? But then we said log of the product would be the sum of the logs. So that would be the sum of the log of x in base 3 plus the sum of the log of y in base 3. Log of x in base 3 is 2. And log of y in base 3 is 4. So that'll be 2 plus 4. And the answer will be 6. So again, we are using the property that the log of the product is the sum of the logs. And then I think we have like a log in base 3 of y over x, right? So now when you have a division, a log of a division, that will be the log of the difference. I mean, difference of the logs, sorry, difference of the logs. So that's the difference of the logs. But in the top here, we have y. So that's actually, that will be log of y minus the log of x. Because y is in the numerator, right? So then we start with the log of y. X log of y in base 3, again, it's, this is y here, sorry. Log of y in base 3 is 4. So that'll be 4 minus 2 equal to positive 2. So the positive 2, that'll be the answer. Of course, it's 4 minus 2 because log of y, as I said, it's 4, and log of x is 2. So well, that's 4 minus 2. Now, if you have the other way, if you have log of base 3 of x over y, then x in the top, so we start with x. So it's log in base 3 of x minus the log in base 3 of y. So that would be log of x, it's 2, and minus log of y, it's 4, and then the answer would be negative 2. Okay, so that's different. Yes, Lord. So it's negative 2, it's different. Now, final one, it's, we need to find log of x, I think x cube, yeah, x cube over y squared. So last one here, log in base 3 again, but it's x cube over y squared, right? So here we have like powers of x and y, and we have like a division, right? So x cubed divided by y squared. So first, because it's a division, log of a division is a difference between the logs. So this is actually log in base 3 of the top, which is x cubed, minus the log of the bottom, which is y squared. So like log in base 3 of y squared. Okay. Well, I don't know what's log of x cubed. I do know log of x, right? I know log of x is 2, but this is log of x cubed. But what I can do here, I can, because it's log of x cubed, I can put down this power of x in front of the log. And the same here for this square. I can put the 2 in front of the log here. So that would be like 3 times log in base 3 of x minus 2 times the log of y in base 3. You see, guys, first you have a division, so then you have like this is subtraction, and then you can, put down the powers in front of the logs. So this is actually 3 times log in base 3 of x, that's 2, minus 2 times log in base 3 of y, that's equal to 4. So that's 4 here. So that's 6 minus 8, and the answer is negative 2. Okay. All right, guys. This just is there any question about this? Anyway, I know it's a lot. I mean, tomorrow we're gonna do
More homework are you gonna put?
Excuse me.
How many more? How many
More homeworks. I think there will be one more homework.
One
Yeah, there will
more?
be one more. Yeah, one more to go. Yeah. In the excuse me.
Good, good.
Yeah. Well. Yeah. In the last minute, guys. Of course, tomorrow we'll continue with this log and exponential, because I'll show you how to solve like more complicated log and exponential equations. But let me just finish this in this last 10 seconds, just to say that you know, there's this exponential with a number e. You know, this e to the x. This is a special number e. E to the x, right? And the inverse, so the log, log in base e, it has a name. As I said, this is like called natural exponential. So log in base e, again, e is just this number, you know, the 2.71, etc. Log in base e of x, as I said, because e is like natural exponential, this is called natural log. So ln of x. So this ln stands for this is natural log. This is what we call the natural log. Okay, so when we write ln, that's natural log, and that means that's the log in base e. And e is this number, the number which is, as I said, is very special because of the derivative, and it's actually 2.7 something. All right.
Let me ask you something. So in the
Yes.
exercise 2, right, you're not doing anything with the initial functions that you have. You're just using the number.
Yeah, I'm just using the numbers because you, for example, I know that my log in base t of x is 2. So like I'm just I substitute this, like this log here of x. I know it's equal to 2. I know that the log of x is equal to 2. It's like given, right?
Okay, it's because I was trying to solve for x.
No. We don't solve for x. I mean, we don't really worry about the x here. I know it's a log of x is equal to 2. It's like given. We don't have to solve for x or anything.
All right.
All right. Thank you, guys. I guess I will see you tomorrow. Please take care, and good night, everyone.
Take care, Professor. Bye-bye.
Good night. Thank you, everyone.
Bye-bye.
See you tomorrow.